In this presentation, we are going to talk about heterogeneous computing systems and partitioned operating systems in space applications. We'll be describing the heterogeneous computer systems, operating systems, going deep into these types of processing elements, and they will be exposing a use case and all the considerations we have to take. Heterogeneous computing systems are systems that are using multiple different processing elements. So they could be general purpose processors, but also FPGAs, DSPs, digital signal processors, neural processing, or GPOS, graphic processing units. They allow for flexible and efficient use of the resources as well, so the ability to handle both demanding hard real-time tasks and computing-intensive tasks. The advantages are high performance, so certain algorithms could run faster in a cluster, of course, with symmetric multiprocessing in general purpose processors. But also some of those tasks could be run more effective in dedicated processing elements as the ones we mentioned before. They also, one of the benefits is flexibility. So you have more different places to allocate all your software requirements. The robustness is implicit. So you have more options where to deploy those software requirements. So they could be in two different processing elements. And in such way, you have implicitly achieved the redundancy. The energy efficiency. When designed for a specific task, some of those processing elements could be switched off or on as needed. So moreover, when we have these systems integrated in a single system on chip or a system model, we could also reuse some of these power supply systems. The implementation of the heterogeneous computing system for space use cases requires a selection of appropriate processing elements and the development of a system architecture that takes advantage of the strengths of each element. This can be done with a combination of hardware and software. Partitioned operating systems are the type of operating system that's allowing multiple applications or tasks to run simultaneously on the same computing system, but at the same time also maintaining some degree of isolation between them. The characteristics of this is fault isolation and containment. So if one application is misbehaving, it's not affecting the others. A partition operating system can reduce the likelihood of the failures spreading between applications and causing a system-wide failure. Failing is done meaning only to maybe make a new pointer access to memory, but also it could be something like stressing the bus of the system or contaminating the cache in case that the core is being used for another application. In our case, the software elements that are isolated one from each other, we are calling them partitions. In this context, the resource allocation is the ability to allocate specific resources to those partitions. Those can be cores, CPU cores, memory, input-output controllers, ranges of memory, which could be registers or RAM memory, but also time. It's important to take into account. Security is allowing us implementation of security policies specific to each partition. Real-time performance is the capability to respond to events in a timely and deterministic manner. Real-time applications can be given priority over non-real-time applications, ensuring that the resources they need to operate effectively. This is important in a space computing system where real-time performance is critical for such tasks as navigation and control. Maintenance, meaning that updates or changes can be made to one partition without affecting the others. This can simplify the maintenance and reduce our downtime, which is important in space computing systems where the downtime can have serious consequences. All these characteristics are key to allow the consolidation of multiple applications having different level of criticality, either for the functional safety or the security of the onboard equipment, and ensure the required real time. Here we're coming back to the different processing elements we have. We have seen during the different presentations the appearance of DSPs for processing audio, image, and speech, neural networking for AI processing, and GPU. We've seen also the usage for the graphics 2D and 3D acceleration, the usages of vectorial floating units, for example. Of course, the FPGAs are very common in the space industry and avionics, but we are going to focus in the general purpose processors, the place where we can allocate software and where the operating systems are running. So we are going to focus on microprocessors, which are MMU based, memory management unit based, and microcontrollers, which some of them are MPU based, memory protection unit based. When we are talking about memory, we refer to all the locations that can be addressed by a CPU. Might be ROM, might be RAM, might be as well I/O memory. The MMU or the MPUs are the way the processor has to control the access of the operating system and the applications to these types of memory. There is usually one MMU or MPU per core. If we go to the MMU, Memory Management Unit, in the single definition, it's translating virtual memory to physical memory. It's providing to each process, it's given the illusion of a large address space dedicated to a single process. This is making the life of the application processor easier. It doesn't need to care about what physical addressing is he accessing. It's the operating system responsibility to allocate the required access, the required memory, to the physical memory. This is allowing to have multiple, even the same process, to be allocated to memory, because it's the operating system responsible to allocate them in different physical memory, while the process thinks that it has the whole address space for himself. It's actually just restricted to a specific memory range. This is in fact how multiprocessing is achieved. When we combine this with hardware virtualization, we are having another level of MMU. So while before we were saying that processes were living in a virtual address space, when we have another level of MMU, we can make operating systems believe that they are working in their own hardware and their own address space. And that's what hypervisors are doing, putting operating systems in a whole virtual world. Implementation of this MMU is not easy. This consists on a relatively large data structure, some kind of multi-level tree table data structure that's mapping the whole virtual space to physical space. Typically, this requires traveling from these levels up to, for example, in RV8, up to 4 levels to reach which is the physical address corresponding to one virtual address. So it's not a cheap implementation. In contrast with MMU, which is implemented in RAM, all these tables I mentioned are written in RAM. MPUs are way simpler. They are implemented by hardware registers, where it's been all the regions which need to be protected are defined there. With microcontrollers, we don't have the concept of virtual space. There is no translation. Everything is in a single linear address space, and operating system and applications are sharing that linear address space. If there would not be an MPU, all the memory would be visible from one application to the other, from one operating system to the other. It's the MPU which is protecting the access of those other regions. By its complexity, we can see that MPU systems are going to be more deterministic. There is less time to resolve one access. So you're going to have always more determinism, faster boot times. You also have possibility to run cluster of cores in lockstep. By contrast, it's a bit more difficult to make symmetric multiprocessing because usually you don't have level 2 cache coherency between cores. Now we are going to explore a typical use case of these heterogeneous computing systems. We have seen in other presentations during DASIA that heterogeneous computing systems are not something new. They are being already launched. We have seen during yesterday the Nano Explorer device and the NG Ultra, and we have also seen some reference to the AMD Versal, which we have maybe all the types of processing elements we have been discussing during this presentation. We have generic processing units like microprocessors and microcontrollers. We have artificial intelligence units, NPUs, DSPs, and FPGA, everything in the same. This is how an heterogeneous computing system looks from the hardware side. So let's talk about the software side. So how we can take benefit of all this system with an partition operating system. This is PikeOS, or certifies RTOS and Hypervisor. In our operating system, the concept of partition can host from simple control loops up to complete virtualized operating systems. So in each of these partitions, they could run different types of applications, different types of runtime environments. For example, we could run from a POSIX runtime environment to an Ada code could run in this partition to something as complex as a complete operating system hosted in a single partition. And PikeOS, from the microkernel point of view, will see it as just an additional task of the operating system. We provide combined safety and security in the same product with mixed criticality. There is a wide range of supported hardware architectures such as ARM, Intel, PowerPC, Spark, and RISC-V, and it's completely certifiable to the highest safety and security standards. Together with our PikeOS product, we also offer a LinOS, which is an embedded Linux distribution, which is a perfect match for embedding on top of PikeOS. And we also have the little brother of PikeOS, which would be PikeOS for MPU. PikeOS for MPU is sharing most of the PikeOS code. It's based around the same separation kernel, but it's based on an asymmetric multiprocessing kernel. That's mainly because of the reason mentioned before, that usually microcontroller cores are not having a level 2 currency cache. Therefore, it's difficult or impossible to implement SMP with MPU-based devices. All SYSGO products, PikeOS, PikeOS for MPU, and LinOS are sharing the same configuration tool. It's an Eclipse-based tool called Codeo. Both of them are in the process or have already achieved certification for ECSS-A, DOA 172, and common criteria. And both of them are already in space applications. In the diagram on the right, we can see how we have one single instance of PikeOS running in SMP, running on top of the application cores, while we have different instances of PikeOS for MPU in asymmetric multiprocessing running on each of the real-time cores on the right side. Having taken into account the description mentioned before about the Xilinx Versal, which all these processing elements, separation and virtualization capabilities of PikeOS allow for hosting very different functions, such as, for example, on the left, safety relevant functions with real-time requirements, ESS qualified, machine learning functionalities within a hardware virtualized Linux guest operating system partition, using for instance TensorFlow libraries or some other machine learning engine, with image processing, using directly the artificial intelligence engines in the hardware. Also some navigation application related on apex.os, so in some aviation environment. And then the other side of PikeOS for MPU, it can be used to host satellite functions with the strict real-time requirements, for instance, proportional control, AOCS, telemetry and telecommand, and then fault detection and installation recovery. On the R5 cores, there could be also some payload control application in charge of communication and monitoring with the payload software running on the A cores. The combination of PikeOS and PikeOS for MPU allows the integrator of the system to take advantage of the benefits while still respecting functional safety and security constraints. To recap, the use of a heterogeneous computing system, in particular those that leverage system-on-chip or system-on-module that offer the highest level of integration and miniaturization to achieve low swap, size, weight, and power footprints, is one of the most promising trends for nano and pico-solid-states onboard computing systems and mission payload computers architecture designs. The level of specialization offered by such heterogeneous hardware architecture must not be offset by the use of inadequate software platforms. Care must be taken in choosing the most appropriate combination of real-time operating systems, hypervisors, general-purpose operating systems, and middleware. PikeOS and PikeOS for MP allows the integrator to distribute software satellite functions to these specialized units, ensuring the appropriate level of functional safety, cybersecurity, and to fulfill the strict real-time requirements typically required by satellite onboard software.